Last class we have discussed the what a derivation of infinite time linear quadratic regulator problems, and then corresponding optimal controller if you use to the system, then its stability analysis is also studied. So, let us explain or illustrate that LQR problem with a numerical example. So, let us consider our dynamic system which is given is a second order dynamic system, x dot is equal to x 2 of t and x 2 dot of t is equal to minus twice x 1 of t plus 2 x 2 of t plus u of t, and we have some initial condition is given, this is given. So, our problem is to determine a control law. If you recollect that our infinite time regulator problem, our problem is to determine the control law u such that this performing index, quadratic performing index is minimized. The first problem, first is you determine the optimal control law u of t, small u of t, because it is scalar input, small u of t is equal to minus k into x of t, where x of t is equal to, we have a two states are there, x 1 of t, x 2 of t, and this is the controller gain, LQR controller gain, LQR controller gain, and it is nothing but a state feedback. What is the information of the state you know from the system, that we are doing some linear combination of the states will give you the control law u. This is the control law. So, we determine the optimal control law key u of t such that the performing index j is equal to 0 to infinity, because it is infinite time regulator problem or horizon infinite horizon control problem is a x 1 square of t plus x 2 square of t plus twice u square of t whole dt is minimized. You design a control law u of t such that this performing index is minimized, and this interpretation we have already discussed. Suppose this is the input free system, this equilibrium position is the linear system, the equilibrium position is origin is the equilibrium position, and due to this initial disturbance or initial condition of the state, the state x 1 x 2 will deviate from the equilibrium position, and our this interprets, each term interprets that deviation from the equilibrium point, means from the origin x 1 state x 1 over the interval 0 to infinity, that quantity you have to minimize. Not only that, in addition to that, control effort u square u transpose q u transpose r u t, which is here is in this case is twice u square t of this also you have to minimize. So, this is the first problem you have to solve. First part of the problem, first part is that one. Second part of this problem is check, after designing the controller, check the stability of the closed loop. This is the closed loop system, this is thing. Then third part of this problem is simulate the systems or get the response of the system, simulate the system with and without controller. With u t is equal to 0 means without controller, without when u t is equal to 0 without controller, with and without controller, using the designed LQR controller, LQR controller with initial state x of 0 is equal to 2, 4, 2, this one. So, let us solve this problem, and if you recollect our basic steps of solving the LQR problem is, first step is to solve the algebraic Riccati equation. First we have to solve the algebraic Riccati equation. What is the algebraic Riccati equation? So, solution, we are writing solution. So, first we write the algebraic Riccati equation. Our algebraic Riccati equation is, before that you see you have to identify which one is A matrix, B matrix, Q matrix, R matrix. These are the 4 matrices information is required to solve the infinite time regulator problems. So, we have to identify from the system model what is system matrix A, input matrix B, and state weighting matrix Q and control weighting matrix R, that we have to identify. It is easily can be seen from the system equation. We can write it that x dot is equal to x dot t is equal to 0, 1. If you write matrix in vector form is a minus 2, 2 into x of t plus 0, 1 u of t. So, from this one immediately you can write A is equal to our 0, 1, minus 2, 2, and this is B is equal to 0, 1. And if you see this one, if you just if you see this our Q and R matrix, if you see here our Q and R matrix, this matrix we can easily write it, this performance index we have to convert into a standard form. That means, here itself we can write, if you like, if you permit me, I can write it half, because that what is called the performance index, that one we should be half into 0 to infinity. Since I divided by half, multiplied by twice, x 1 square plus twice x 2 square plus 4 u square of t whole dt. Why I have made it half? Our standard formulation, if you say half is there, this half is we have created there in the derivation, because when you will do the partial derivation of this LQR problem, throughout the derivation process, the 2 will come, 2 and this 2 will be cancelled for this one, and based on this one we have derived all our expression. So, that is why I have just, in order to make it into standard form, I divided by half, multiplied by 2. So, this is the standard form. From this equation you see that Q is what, R is what from this. So, our Q is, if you see, this is nothing but a 2, 0, 0, 2, and our R is equal to 4. This is 2 cross 2 matrix, this is this. So, once you know A, B, Q, R, this is the first step, identify A, B, Q, R from the statement of the problem. Once you identify this one, then you can write it. Next step is to check that what is the stability conditions, check the controllability condition. You check the controllability condition, whether you will be able to drive all the states into the what is called desired location, or if the open loop poles are unstable, whether you will be able to drive that unstable poles to the stable poles, mean from the right up poles to the left up poles, whether you will be able to do it or not, that you have to check it, and that is done. Suppose you have a system, before that I am just telling you how to check this one. If you have a system described by x dot is equal to A x plus B u of t, then how to check the controllability of this system? Means controllability of the system means you will be able to drive the state from initial state to a desired state with a finite time, within a finite time, by using appropriate control law, whether it is possible or not. Before that, we can check it whether system is controllable or not. We can check it that you find out the rank of this matrix, rank of, let us call the matrix is W, is how will you form the rank of the matrix? B, A B and dot dot A n minus 1 B, this you form it. This is a n cross 1 n cross n matrix, then state of the system is n states. So, you form a matrix up to A n minus into B. So, find out the rank R, small r is indicates rank of this matrix. If the rank of the matrix is n, the system is, this implies the system is completely controllable. System is completely controllable. The system is completely controllable. That means, all the states we will be able to drive from any position to the what is called any other desired position, that is. So, we will check whether system is controllable or not, at least it should be stabilizable. So, if you check this one, then we will find out that our rank of B A B, in our case rank of B matrix is what? 0 1 is a vector in this case, or you can a matrix of dimension 2 cross 1, this B. Then A B, if you multiplied A into B, that will be coming, say this A into B, this will reflect the last column of that one. Okay. So, that will reflect the last column of that one. So, it will be coming that 1 2. So, that that rank of this matrix clearly is equal to 2, and which is equal to n. In our case, n is equal to 2. If you see number of order of the system is 2. So, the system is controllable. So, this then we can proceed it. If the system is not controllable or at least is not stabilizable, then you have to check whether system is stabilizable or not. Stabilizable means, if you have a open loop system is a unstable mode, that unstable mode should be stabilizable, in the sense you will be able to drive the unstable poles or the eigenvalues to the from the left half from the right half of the S plane to the left half of the S plane. You will be able to drive it by using a control effort. If you satisfy that condition, then it will be told the system is stabilizable. But uncontrollable mode is not controllable, then it is a not stabilizable. Hence, it indicates that we cannot apply the LQR control problems. So, unstable mode, in other sense, you can unstable modes means eigenvalues, unstable modes of open loop system must be stabilizable. So, this is the important thing. So, first if we check the controllability test, if it is completely controllable, we can proceed first. Then our step is, if you recollect one by one step, we have to solve our algebraic Riccati equations. Since it is the infinite time regulator, the time is 0 to infinity in the performance index integral part, 0 to infinity. So, it is the infinite time regulator problems. So, our equation is H transpose P plus P A minus P B R inverse B transpose P plus Q is equal to 0, null matrix of dimension n cross n. We know A, B, R, Q. So, only unknown is P, you have to solve it by some means. We will discuss in details what are the different methods are there to solve the algebraic Riccati equation. For the time being, we will just use, since it is a smaller dimension 2 by 2 or 3 by 2, we can do algebraic solution of this one, because we will get a set of nonlinear equations, set of algebraic nonlinear equations. Then how to solve this one with a smaller dimension, we can do it with a hand calculation. Let us see. I will put the value of that one, A transpose. A is what? This is the A transpose, you write it. So, this will be a 0 1 minus 2 2 A transpose, and then P is a symmetric matrix and positive definite, solution you should get positive definite. P 1 1 P 1 2, since it is a symmetric matrix, P 1 2 is equal P 2 1 is equal to P 1 2 P 2 2 plus again this one P 1 1 P 1 2 P 1 2 P 2 2, then multiplied by A 0 minus 2 1 2, this is that one P A, all this in, then minus P I am writing P 1 1 P 1 2 P 1 2 P 2 2, P B is what? 0 P B 0 1, then R inverse, R is 4, the R inverse is 1 by 4, then B transpose is 0 1, then multiplied by P. So, this cross I am writing here, next page, cross multiplied by, that is our P is P 1 1 P 1 2 P 1 2 P 2 2, then plus Q is a diagonal matrix, each element is 2, if you see. So, this and right hand side is equal to 0 0 0 0. Okay. So, now you see you multiply by this into this, A transpose P, unknowns are 3 unknowns are there, 3 equation, at least we are getting 3 equations. So, we will be able to solve, but when you will equate left hand side into right hand side, you will get in general is nonlinear algebraic Riccati equation. Agree that we have to solve it. So, that you multiplied by this into this into this is a minus 2 P 1 2. So, I will write it left hand side minus P 1 2 is equal to so, first we will write it minus this, you see this into this into this. So, it will be a minus 2 P 1 2, then it will be next is this row multiplied by this minus 2 P 2 2 minus 2 P 2 2 minus 2 P 2 2, then this row multiplied by this column P 1 1 twice P 1 2 P 1 1 plus twice P 1 2, then this row P 1 2, then this row multiplied by this P 1 2 plus twice P 2 2. Agree? So, this and this part, this is A transpose P, this one, and this we have shown this value. Now, look at this one cannot solve, one not necessary to solve P A. So, P A is nothing but a transpose of this one. Once you got the product of this one, take the transpose to get P A. To take the results of that one, A transpose P, take its result transpose, then you will get P A. So, I will take the transpose of that one. So, this will be a minus twice P 1 2 minus 2 P 2 2 P 1 1 plus twice P 1 2, agree, then P 1 2 plus twice P 2 2. So, this quantity is nothing but a transpose P, transpose of this one is nothing but a P A, transpose of that quantity is nothing but a this one. So, you can avoid this competition by taking transpose of this one and write it for the value of P into A, that one. So, next is if you see you multiply it by P B R inverse B transpose P, agree. If you do this one, this second part of this one, that P B, if you multiply it by this, you will get the last column of P, because you see this 0 1. So, it will come last column of this one, this into this into this. So, ultimately it will come from this one last column of this one, that will be P 1 1, P 1, that will be P 2 2, agree, that multiplied by R inverse. R inverse is what, 1 by 4, that means 0.25, agree. Now, you see this one B P B R inverse, and P B, if you know it, if you take the transpose of that one, B transpose P. So, this you need not to compute, from the knowledge of these results I can write, take the transpose of P B. Then if you take the transpose of P B, I will get it P B transpose P. So, this is P 1 1, P 2 2. Then multiplied by what is this, P B transpose, then P. P B transpose we have done it. So, this part is over. P B we have calculated, R inverse is 1 by 4 means 0.5, and transpose of this one we have calculated this, plus Q. Q is 2 0 0 2 is equal to 2 0 0 0. Now, now you element wise left hand side, right hand side you equate. This element means A 1 1 position. So, you add this one plus this one, plus after multiplying by this you add it. So, if you see that quantity, this quantity after multiplying by this, it will be a 1/4, this is 1/4 means point, minus 0.25, and this is nothing but a P 1 1 square, P 1 1, P 2 2, this, then this will be a P 1 1, P 2 2, then P 2 2 square. I am writing this quantity only. So, just like now adding this A 1 1 element, A 1 1 element, this one is this one, A 1 1 element, then A 1 element is equal to that one. So, element wise if you equate now, you will get it element wise. So, I am getting 1 1 element, left hand side and right hand side. If you equate, I am getting minus 0.25 P 1 square minus 4 P 1 2 plus 2 is equal to 0. You see this and this 4, this is 2, 4 2, and this is coming 0.25 P 1 square, 0.25 P 1 square. What is this? This this is, I did mistakes here, you just see here, if you multiply it by this and this, that this and this, if it is P 1 2, this row multiplied by this, it is P 1 2, this row multiplied by the P 2 2. So, it is not a P 1 1, P 1 2, agree. So, this is also P 1 2. So, this will be coming P 1 2, if you multiplied by this is P 1 2, agree. So, now I am getting 0.5 P 1 2 square plus 4 P 1 0 1 element, then I write it 2 2 element, 2 2 element. 2 2 element is that one, you see this plus this is the 2 2 element, this is the 2 2 element, and here 2 2 element is this one, plus 2 2 element is 0, here is right hand side 0. So, if you see the 2 2 element minus 0.25 minus 2 P 2 2 P 2 2 square, then you will get it twice, see this one P 2 2 element, P 2 2, then this. So, it will come now I am telling, sorry, that P 2 2 element, that means forget about, not this one, P 2 element is that one. So, this one, and your case is that one. This is the P 2 element I am writing. So, this is 0.25 P 2 square, 0.225 P 2 square, what we have written it. Then this twice, here is this one P 1 to 2 P 2, then P 1 to 2 P 2, the twice of this one plus 2. So, I am writing this one twice of P 2 plus 2 P 2 plus 2 is equal to 0. This is another equation. Now, I am writing either P 2 element is same as P 2 element, because it is a symmetric matrix. So, now in this case you see what is that quantity. P 2 element is this one, agree, this one, then this one, and this is this one, and this is 0, this one, and this is this one. So, if you write it that one, I can write it P 2 elements are that minus, this is 0.25 minus 0.25 P 2 whole square, then your minus minus 2 P 2 P 2 minus 2 P 2, then your plus P 1 plus twice P 2 is equal to 0. Just I am writing this quantity 2 element. 2 element is 0.2 P 2 P 2 P, yes, 2 element. This is P, this is I think P 2 element minus 0.25 P P 2 P P 2 this quantity, and then I am writing, then I am writing P 2 P 2 P 2, then I am writing P 2 P 1 plus twice P 2 twice P 2 this. So, our I am writing clearly this one 0.25 P P 2 agree, then minus twice P 2 plus P 1 plus twice P 2. So, you have a 3 equation 1, 2 and 3 equation, and these 3 equation if you solve it, you will get the solution of P 1, P 2, P 2. So, let us solve these 3 equation, then what we will get it, let us solve from equation 1, from equation 1 what we can write it, this is a quadratic equation, we can write P 2 is equal to, that is minus b plus minus root over. So, if you just divided by multiplied by what is 4 both side, then it will come this, if you multiply by both side by 4 minus 4, then P 2 square minus 16 P 2, this is minus plus minus 8 is equal to 0, that quantity is that one. This if you multiply it by minus 4, then this will be plus minus. So, it will be minus b plus minus root over b square means 16 square minus 4 a c divided by 2 into a. So, we will get this, if you solve it, you will get two values of P 2, that is value is 0.485 or I will get minus 16.485. So, out of these two, whether we have to accept both the values or one of them we have to accept, that we will see later stage. So, let us see, once I know P 2 from equation 2. So, from equation 2 I know P 2 value here. If you put a P 2 value here, you will get a quadratic equation in P22 form, okay, quadratic equation P2 form. So, if you just put the values of that one P, that expression, once again I multiplied by -4 both sides, -4. So, it will be coming, if you multiply it by -4 both sides, it will be coming P22 square minus 16, okay, 16, then it will be P22, this is 2, 16 how it is coming, 2, 2, 4 multiplied by 4 means it is a 16 minus 16 P22 minus 8, I am multiplying by 4 minus 4, the minus 2 is there. So, minus 8 P12 minus 8 P12, P12 value is what? If I consider 4, 8, 5 first, this is the P12 value, and minus next is minus 8 is equal to 0. This is minus 4 both sides, this is minus 4 is equal to 0. So, ultimately our equation is that one, P22 square minus 16 P22 minus 11.88 is equal to 0. This is the thing. So, the solution of this is equal to 16 plus minus 256, 16 square minus 4 into A into 11.88. So, there divided by twice A, and that value we will get two values of this one, 16.711 one value, and another value will come, what is called, this is plus plus minus. So, it will be what is called minus sign will preceded with a, that minus more than 16 you will get. So, this next quantity will be negative term, agree, one can easily find out that negative term is what. So, this negative term cannot be considered, because our, if you the Sylvester inequality test, if you see a matrix should be positive definite, first condition is all diagonal elements must be positive, but here the other values of p roots are negative. So, we cannot discard the negative values of P22, discard the negative value of P22. Okay. So, we will consider this one, and this is a positive definite. This is the one value of P12, which is 0.85 0.485. Suppose if you consider the value of P12 is that one, then you will get solution of P2T is complex. So, we will not consider that values. So, this will give you the, will accept that value, accept, and this will give you, this will give the solution, this will give the solution of P, what we got, P22, this will give the solution of P22 complex value. So, we will consider our, this is the, we will accept it, P value is this one, P22 value. Once I know P12 value and P22 value, once I know P22 value and P12 value, immediately I can find out from equation 3 the P11. This is known, P12 is known, and which value we have accepted, that we know, and we can get the solution of P11. So, from 3, using P12 is equal to 0.485 and P22 is equal to 16.711, and we get P11 is equal to 0.25 P12 P22 plus 2 P22 minus P12, that is equation number 3. So, this equation once again I multiplied by 4, that will be a minus 4. So, this will 4 p 1 to this, or as it is you keep it, does not matter for this one. So, 0.25 p 11 p 22, if you take that side, agree that p 12 p 22 values, this p 22 values, this and p 12 values, twice p 12 values. And from this equation you see one can write it this equation p 12 this, if I take that side 0.25 p 11 p 22, which I have written in that one, then it is a 2 p 22. If you take that side is a plus p 22, then your twice p 12, just see this one p twice p 12, equation to twice p 12, again then p 11. So, minus twice p 12, this is twice p 12, again. So, if you use these values of this, then p 11 value you are getting 34.48 p 12. From this equation I just find out this is the only unknown thing, this is the unknown. So, I can get by using the values of p 1 to p 22 value with appropriate values of p 1 2 and p 22, and now you check it, P should be a positive definite matrix. So, P is p 11, p 12, p 12, p 22. So, if you put these values of p 12 34.48, then p 12 is minus 0.485, then 0.485, then 16.71. So, and that matrix is positive definite matrix. You can check it either finding out the eigenvalues of this matrix, all eigenvalues will be a positive, or you can use the Sylvester test for testing the what the matrix is, whether matrix is positive definite matrix or negative definite matrix, or positive semi definite matrix or negative semi definite matrix, that can be checked by using the Sylvester inequality conditions. So, our case is P is greater than 0. So, positive definite matrix. So, this implies that the controller, the way we will design the controller will stabilize the systems. So, let us find how to find out the controller gain. Okay. So, controller gain. So, you know K is equal to R inverse B transpose P. You just use the values, R inverse means 0.25, B is 0.1 and P is just now we got it, it is a 34.48, 0.4085, 0.485, 0.485, and that we got 16.71. If you multiply it by this last row will be reflected. So, 0.25 into last row, 0.25 into 0.85, 16.71. So, multiplied by 0.4, but or divided by this each element by 4, then you will get it, this is 0.121, then 4.178. So, this is the controller gain. So, this is the controller gain we got it. So, once you know the controller gain, immediately I can find out the control law, and which is nothing but a u of t is equal to minus x of t. We assume that these are all accessible, measurable by the users, this one. So, you know k, immediately you can implement u of t. So, u of t is nothing but a minus 0.121 0 not 0 4 point, just now you got it 4.178 this into that our x is x 1 of t, x 2 of t. So, this is our control law, and if this control law you apply to the system, then it will stabilize the system. Not only stabilize, it will drive the state to a what is called equilibrium position from the initial state x t 0 to the equilibrium position, agree, in a optimum manner by minimizing the that performing index. So, our check the closed loop system stability. So, our x dot is equal to A is equal to A of x t plus B u of t, and if you put the value of u of t is equal to minus k x of t, and our closed loop system will become, you take the x of t common, then b of k is x of t, and this nothing but a suffix c x of t, and this is the our closed loop system matrix. Now, system is stable or not, you just find out the eigenvalues of this matrix. If eigenvalues of this matrix with a negative real parts, then system is stable. So, find out the what is called eigenvalues of this matrix, the closed loop systems. The part 2 is the, if you see the part 2 of the problem, our the check the stability of the closed loop system. Part 2 of the problem is check the stability of the closed loop system. So, you find out the eigenvalues of AC matrix. AC means A minus B k matrix. If all the eigenvalues of this one with negative real parts, the system is stable. So, find out, it is just we know how to find out the eigenvalues, the determinant of AC minus lambda I of this equal to 0, and you will get, because AC is known, lambda is unknown. So, you will get a polynomial of order in general n, where n is the dimension of the system matrix or dimension of the state variables. Agree? So, this will be the order polynomial you will get in terms of lambda, which order will be n, same as n is the order of the system matrix. So, you just find out first is AC, AC is our A, and A is what 0 1 minus 2 2, and B is your 0 1 and your k, we got it 0.121 4.178. So, now if you simplify this one, ultimately you will get this matrix is 0 1 minus 2.121 minus 2.178. This is the closed loop systems. So, the eigenvalues of this one, how will you find out? So, determinant of what is called matrix AC minus lambda I is equal to 0. So, if you do this one, so I will leave it exercise to this one, it is nothing but a AC symbol is lambda I of this equal to 0. If you do this one, you will get it, the determinant of lambda square is equal to plus twice 0.178 lambda plus 2.121 is equal to 0. That eigenvalues of these two will be, this is quadratic equation minus b plus minus root over b square minus 4 a c. If you do it, you will get it minus 1.01 plus minus 0.967 I. So, this is the, and this real part of this one is negative. So, system is stable. That means, with the application of this controller, the system response will be stable, means it will bring back to the state from initial state to an equilibrium state. Agree? So, so our conclusion, this implies that the closed loop system designed with LQR approach stabilize the systems. The closed loop system designed with the LQR approach stabilizes So, this is our conclusion. Now, third part of the third part of the problem is, if you see, it is nothing but a, that is what we call find the system response, with the application of that what is called LQR problem, optimal control law, and optimal control law is designed based on the LQR. So, you are asked to simulate the system, get the response t versus you find out x 1 of t, then x 2 of t. This is. So, our initial state, if you see, it is a x t, if it is a 2, this is 4 0, and it is a 2 4 6 8 10 12 and 16, something like this. Then our initial state is starting from that our x 1 0 is this one, this is the initial state for x 1 of 0 is equal to 4. This is the initial state x 2 of 0 is equal to state 2. By using this what is called control law, you find out the response of the systems. Let us call response of the system, just say you have to solve it. How it would solve it? X dot is equal to A x plus A x of t plus B u of t, agree, or you can write A x minus B k of x t. So, it is a solution of autonomous system, that autonomous system is the closed loop systems. You know the value of given x top x t 0 is equal to x 0 is given. So, you can solve this one. So, let us call the solution may be like this way, ultimately to come 0, and this is the solution of other state solution may be like this way, it is coming to 0 like this. So, you find out the response of this system and you know the this matrix and you can solve it. So, this is I leave this in an exercise to solve this one. Now, let us see with closed loop control system how it looks like in a block diagram form. So, if you see our system is, this is our f integration, this is the integration, and this is our x dot 2 x dot of t, output of this is the integration, agree, output of this one is x 2 of t, which is nothing but a x 1 dot of t as per the description of the system dynamics, and that goes to the integrator, agree, this goes to the integrator, and the output of the integrator, this is the integrator, agree. So, output of this one is x 1 of t, and this output is going to the minus, and this is the summer, and x 2 is multiplied by 2 gain 2, you can say x 1 is gain 2 amplify, you can realize this one is an amplifier, this is the your plus, and this is state information is minus 2, and then it is this. So, this is our, this portion will be x dot is equal to A x. So, you have a B u. So, you have a this. So, x and x 2 information must be available to the controller. So, our controller, this is one, so this is our x 1 of t, and this value is what, point 121, and this value is your, this value is 4.178, this is our x 2 of t. So, these two signals multiplied, and then it is a minus k x negative, and this multiplied by your B u, and what is our B u, and this is u is coming only the, you see the dynamics of that one. u is coming only in the second state, that makes 2 dot expression. So, this directly I can write it, this is nothing but our u of t. So, if you see this portion from here to here, this is our plant or system, and our controller is that part. This is the controller. That is the controller, and this controller is what? What type of controller? That controller is LQR controller. So, one can look at this expression, one can change the controller gain by selecting the state weighting matrix Q and R. This is only the tuning parameter designer have. That I can tune the controller parameters, that K values, by tuning the Q and R. So, if so long our response is not satisfied, we can always tune Q and R to get the desired response of this one. So, this is this scheme is the infinite time LQR problem solution. This is the thing. Let us now go back to what is we call the how to solve the what is called the algebraic Riccati equation, how to solve the algebraic Riccati equation by different techniques or different methods. Solution of A.R.E. algebraic Riccati equation, solution algebraic equation. So, first method is the simplest method, but it takes much time to get the converse value of p. So, method 1 is the iterative method, So, A.R.E. solution. So, what is our A.R.E. equation? A transpose P plus P A minus P B R inverse B transpose P plus Q is equal to null matrix of dimension n cross n, where n is the order of the system matrix or the number of states in the systems. This is n. So, this we can rewrite into this form. Look carefully how we am writing this one. A minus B R inverse B transpose P whole transpose P, then plus P A minus B R inverse B transpose P, this plus Q plus P B R inverse B transpose P is equal to null matrix. Now, we would see this manipulation we have done also earlier when you have discussed the finite time regulator problems. What I did it here, this term is this and this term I have written A transpose, if you see A transpose P, this term is there, then this will be a transpose then multiplied by P. So, it will be a P, then it will become B R inverse B transpose into P. So, I am getting that one. You know this A B C whole transpose is equal to C transpose B transpose A transpose, that properties I have used it here. So, this is that equation, agree. Then this equation, then I am P A, this is I can write P A minus P R inverse B transpose P, this. So, this is one term I have taken more. So, I have added P B R inverse B transpose P. So, this cancel, as ultimately this remains same. So, this I am writing into this form A minus B R inverse B transpose, let us call this is I am writing P suffix k, kth iteration the value of P transpose P k plus 1, then P A minus B R inverse B transpose this is I am writing k plus 1, k plus 1 is iteration, this is k is equal to, if I take this is my that side is equal to q, then p k b R inverse B transpose P k. What is the k indicates? The kth iteration, what is the value of p? Let us call starting iteration is 0th iteration p of 0, and this is means next iteration what is the value of p, that is k plus 1. In this way I have just inside the bracket is a kth iteration, outside the bracket is p value is k plus 1th iteration in this way. So, now you see this matrix Q is positive definite matrix, positive semi definite, R is positive definite matrix. So, this product will be, because it is multiplied by some matrix, then positive definite matrix and transpose of that matrix, post multiplied by transpose of pre multiplied matrix. Okay. So, this matrix in turn the whole matrix is a becoming a positive definite matrix. So, positive definite matrix and positive semi definite matrix result will be a positive definite matrix. So, it is something like a standard Lyapunov function method function. If you consider, then in order to find the stability of the autonomous system, we know our condition is A transpose P plus P A is equal to minus Q. You assign some positive definite matrix. If A is stable, then solution of P must be positive definite. So, that we are using here. So, our expression now it is coming, if you see, if I consider A k, this is the whole thing is A k transpose P k plus 1 plus P k plus 1 A k is equal to minus that one Q plus P k plus B R inverse B transpose P k. So, this please note down what I am written here. Suppose if you have a x dot is equal to a x is there, you want to study the stability of the system by using Lyapunov function method, then our condition is that this solution, if you do the solution of this one and with a assigned value of q is equal to positive definite, q is positive definite, if you get the solution of A is if you know A, P, if you get the solution of P is positive definite, it indicates the matrix A is a stable matrix, means all eigenvalues of A matrix is negative real parts. So, here also how to solve this iteration, this one k is equal to 0, 1, 2 dot dot in. When is equal to k is equal to 0 means P of 0. So, you assign P of 0 value positive definite matrix in such a way, so that this matrix is stable. So, you choose initial value of our Riccati equation solution P in such a way P 0, so that A minus B R inverse B transpose is stable. Then this is, I just mentioned this is a positive definite matrix. So, this is a stable matrix, this is a positive definite matrix, then the solution of this one I will get positive definite matrix. Whatever the you got it this positive definite, use it here once again, agree, then you solve this equation and repeatedly you do, and you will see finally that you will get the solution of P as k tends to infinity, P is converts to a constant value. That we will discuss in detail next class, that convergence of solution of recursive manner, if you solve it, the convergence of this one solution exists and it tends to a some constant value. So, here I will stop it.